Let's not forget our experimental techniques. Remember, you've got aim, hypothesis, and investigative question. They generally ask for hypotheses, but all of them, you're always going to have to link the independent and dependent variables. For a hypothesis, it's a statement. For a aim, you always start with the word to. And for an investigative question, you're going to need a question that links the independent and dependent variables. What are the independent and dependent variables? I change the independent variable, so it's what the experimenter manipulates. The dependent variable is the thing that we measure. So it's whatever's being measured is the dependent variable. We may use that then to get some calculations later on, but that's what we're measuring. And fixed variables are all the things that we need to keep the same so that we get something called a fair test. So that's only one thing may change, and that's the independent variable. As a result of that one change, only one other thing changes, and that's what I measure. Remember, when you're looking at your data, if your data is close together, then you've got precise data. That doesn't mean it's correct data. It just means that all your information is close together. It usually means that you've got better data if it's close, but you could have been making the same mistake over and over again. Accurate means, oh, there are a lot of C's there. Accurate means that you've actually got the correct answer. So, for example, let's say you got 7,2 meters per second squared, 7,1 meters per second squared, 7,4 meters per second squared. You would have some precise information on gravitational acceleration, but it would not be accurate. However, if you got 9,3, 9,7, and 10,1, it wouldn't have been as precise, but those would be more accurate answers for gravitational acceleration. Remember, when you're plotting graphs, you always give it a heading, graph of y versus x, whatever's on the y-axis versus whatever is on the x-axis. You then label and scale your axes. Remember, scaling your axis, start at 0 and then choose an appropriate scale that goes up in even units. Don't forget to put units onto your description for your labels on your axes as well. If you get a straight line graph, what have you got? You have got a direct proportionality, and this is an exponential graph. And you can also get an inverse proportionality if you get some sort of a hyperbola. That's an inverse proportion. This is an exponential ratio that things are going up in. How do I calculate something like a percentage error? Let's say, for example, I have got a gravitational acceleration value of 9,6 meters per second squared. But we know that this is the experiment, and we know that the real value, or the correct value, is 9,8 meters per second squared. What is the percentage error? What I do is I say, what's the difference between these? The error part is 0,2. 0,2 out of 9,8. So 9,8 is the perfect answer, but it's 0,2 away from there, and then I times that by 100 in order to get a percentage error. So in this particular case, I would land up with, it turns out to be a 2% error. So that's how you would be able to calculate the percentage error. Obviously, with all of these experimental situations, you get something that's totally unfamiliar. You need to read carefully to see exactly what they are asking you is being changed by the experimenter versus what is the experimenter going to measure versus what needs to stay the same for that all to be a fair test. And then interpret the data on its merits each time. These are always thinking questions. They're not particularly difficult, but they are quite difficult to study for and to prepare for.